Okay, welcome everyone. It's great to see so many of you here in the room and also online, of course. Welcome to our first colloquium in this academic year. It's a pleasure to welcome today Tilman Pfau from the University of Stuttgart. Let me introduce him briefly. Tilman studied in Constance and did also his PhD in habilitation there in the group of Jürgen Müneck. He moved to Stuttgart in 2000, where he became a full professor, and in 1999. And in 2000, he became director of the 5. Physikalisches Institut there, and in 2014, he was founding director of the Center for Integrated Quantum Science and Technology. I will not go through the list of prizes. He won an ERC advanced grant, and his research covers a really broad range of physics and quantum optics with cold and hot atoms, in particular on dipolar quantum gases and all kinds of incarnations of Rydberg physics, with applications from trace gas sensing up to quantum computations. And we are very much looking forward to your talk. Please.
Okay, thank you, Clemens, for that introduction and the invitation to come here again. Yes, coming back to a lot of friends. I'm not sure how I get rid of this upper line here, but I can read the title to you. It's about, huh? Yeah, I tried intermedia. Yeah, and Namen, Video Panel ausblenden. This? Ah, okay. Okay, good. Yeah, so that's the title, Dipolar Quantum Droplets and Supersolids. That's one of the activities that we have in my group in Stuttgart, and it's a long-standing common interest with Louis here, and also Silke and Henrik and so on. Many people worldwide now do dipolar physics. Yeah, but this whole field started actually more than 20 years, or almost 25 years, I must say by now, with the ideas around magnetic dipolar gases. And why is it so interesting? Well, you see this kind of movie here, yeah, that shows a classical ferrofluid, yeah, made of magnetic particles that undergo a magnetic dipole-dipole interaction. Yeah, and what you can see here is that all kinds of fun stuff is happening. Yes, a lot of structures are forming, in a lot of dynamics can be studied, yeah, and so on. And these ferrofluids, the classical ferrofluids, if you have never seen them, yeah, you should really go to some science museum and play with them. Yeah, is what motivated us very early on, yeah, to study this in the quantum world. Yes, because now we are going to see a Bose-Einstein condensate, which is a superfluid, yeah, that shows similar kind of behavior. Okay, so that's the very short introduction. And if you wonder where all these nice movies come from, there's a lot of them actually produced by some artists here. And the word that you have to type in YouTube is chemical bouillon. It's like a soup. Yeah? Okay, so this is the group. Oh, wow, there's a memory of the beamer on the previous slide. Which, you know, we like to go to the mountains and so on. And of course, we are looking for people, as everybody, like you guys as well. Just very briefly, before we go into this topic, of course, at my institute, we do a lot of other things as well. Besides the experiments with these interacting atoms and molecules, I should say, yes, because Tim Langen is part of my institute working on calcium fluoride and barium fluoride. We recently also started some activity in quantum computing and simulation with ultra-cold atoms. And as Clemens was saying, we also work with vapor cells, which are atoms at room temperature or even above, which you can use for sensing applications or for nonlinear quantum optics in integrated photonic circuits. I'm not going to talk about this, but if you're interested, check out our website here. Just very briefly, this Rydberg quantum computer project, you know, is is sort of new. And if you are interested, what we are doing, we are working on the Rydberg platform. So, and as we are from Baden-Württemberg, which formerly was known under the word the Ländle, now we have changed this, and now it's called the land. Yes, I don't know whether you have heard about this PR activity of our local government. And according to this, we have now defined, of course, the quantum land. And that's our activity on Rydberg quantum computers and simulators made in Stuttgart, of course. And if you want to play around with a Rydberg quantum computer, you can do it already now. In this website, you can register and you get a key, yes, an API key, yes, to use the emulator that we have set up for that Rydberg platform, which is, of course, a little bit different than, for example, the iron platform that is worked on here. And I don't know whether you have an emulator, but these emulators or the real machines can start to compete now, yes. And you can see, you know, who wins and who is faster for certain tasks or more efficient. So if you're interested in this, check this out. But now coming to the topic of today's talk, we are going to talk about a very dilute gas of magnetic atoms that are represented here in real space, yeah, and they have an interaction. Actually, they have two interactions. One is a short range, let's say hard sphere kind of interaction. And the other one is a longer range anisotropic magnetic interaction that you know from if you put just two magnets side by side, then they repel each other or attract each other depending on their relative orientation. Okay. So this is the picture that you should have in mind. Note that in our experiments throughout the talk, the magnetic dipole moments will all be oriented by an external magnetic field to point in one direction. Yeah, so the dipoles are not like randomly flipping around, they are fully magnetized. Okay. What we can do then is what you know also from the work here, for example, in Silke's group, is you use a Feshbach resonance, yeah, and you change the short range interaction, meaning you are changing the so-called scattering length, yeah, which means for these magnetic systems, you can change the ratio of the long range to the short range interaction within one atom, just by tuning a magnetic field, okay? So you can investigate phase transitions from a contact interacting to a dipolar interacting system, for example, by using that control parameter. And we will see that in a minute, how this works. Now, here's another movie of these classical ferrofluids, yeah, again, from this chemical bouillon, the soup website. And what you see here is that there are interesting structures that are forming, yes. And in physics, you find this kind of pattern formation in many different situations, yes. Note that there was this labyrinth kind of structure, yeah. And you can ask, where else in nature do I find such structures, yes. On the left side, I showed you, this is what a classical ferrofluid looks like. Sometimes it looks like an array of droplets, but you can also find parameters where the ferrofluid is a connected fluid with a lot of holes, yeah. Or in other parameters, you saw this in the movie, it shows a labyrinth kind of structure, yes. You find this in nature as well, yeah. I mean, if you look at the skin of some animals, yeah, you find some animals here, like a fish, yeah, that has a labyrinth on his skin, yes. Or you find a connected pattern of white color on the giraffe, yeah, that is separated by holes. Or you find, of course, some animals with an array of dots, yes. Or if you go out to nature, yes, and you watch the grass, in the desert, for example, yeah, you can find arrays of dots, arrays of holes, yes, or some labyrinth structure, okay. Very general phenomenon, yes. Pattern formation, that's what we mean by the investigation of pattern formation. And there are lots of other cellular automata, and in nuclear physics, they call this the nuclear pasta, yeah, this is also a sort of phase transition that happens within the nucleus, yes. And what we are going to talk about mostly is a quantum ferrofluid in quotation marks, which also shows this kind of behavior. Yeah. Again, you have an array of droplets, array of holes, and a labyrinth structure in certain ranges of parameter space. Okay. Just as another example of fun, this is a colloquium, yeah, so we can have some fun. Yeah. Another example of a pattern formation mechanism. Yeah, it's very simple. It's a mathematical physics problem. Think about a lawn. Yes, a piece of land with grass. Yeah, it's green here. Yeah, it has the area 1, let's say, square meters. In the mathematicians, they forget about the unit, but let's say the area is 1. Yes, and then there is a grasshopper. Yes, that lives on this lawn. Yes, and he likes to jump. And when he jumps, he always jumps a certain distance, d. This distance is smaller than 1. Yeah? Otherwise, he would always leave the lawn. Yes? So it's smaller than 1. Yeah? But now the task is, what is the best suited shape of that lawn, such that the probability of this grasshopper to land back on the lawn, yeah, is maximized. So you see that if the grasshopper starts at the edge, yeah, that's where it's particularly interesting, at least for small d's, yes, then he will most of the time actually land outside. That's not good. Yeah, you want to keep the grasshopper happy, and he should come back to that lawn as often as possible, with the highest possible probability. And the question now is, what is the optimal shape for this lawn? Yeah? And you find the solution in this paper by Olga Gulko here from MIT in this paper. And you see that something interesting happens actually at the surface of that lawn for small d's. Yeah? So she calculates this optimal shape, and she finds that with this length scale d, there starts to be a corrugation at the surface of that lawn. Okay, for small d's. Yeah, and then she basically increases the d. Yeah, and you see that the corrugation at the surface, the period of this starts to increase, corresponding to the length scale, the only length scale in the problem, which is d. Okay. But what is even more interesting, if you increase this d above a certain critical number, then this lawn starts to fragment into patterns, yes, that look very much similar to these labyrinths or stripe phases, you know, that we find in other systems. So here is a phase diagram of this optimal lawn as a function of d. Remember, the area is 1, yeah, so the d doesn't make sense if it is larger than 1, but any value smaller than 1 makes sense. You get a maximum probability that, of course, drops the further the grasshopper hops. Yes, so the maximum probability to land back in the lawn is going down, but the optimal shape now, yeah, comes in various various patterns. Yes, and there are critical values of that d, where you make a transition from that cogwheel here to stripes, 3-bladed fans, and so on. Yes, so that's just, you know, an observation. Yes, wherever you have a length scale, yeah, that you have in your problem, in this case the hopping distance of the grasshopper, there is structure formation happening on this length scale. Yes? Okay, you can think about this. We can discuss about it later. It's not my topic, but I like this example because it shows you that pattern formation is a very generic phenomenon in physics. Now, I show you a phase diagram of this quantum ferrofluid that we calculated, the ground state phase diagram for a 2-dimensional quantum ferrofluid, yeah, of the type that we are going to see in the experiment, that resemble some of the features of that movie here. Yes. What I'm plotting here is the contact interaction, the scattering length. Remember that yellow sphere, yeah, that has a different size with which we can scan with the Feshbach resonance here. Yeah. And then the other parameter we have in a certain harmonic trap is just the atom number. Yeah. And if we vary this, well, for very large contact interaction, we just get a Bose-Einstein condensate. Yeah, it's a boring distribution. It's just flat. Yeah. So it looks like this maybe a little bit. Yeah. Then if we reduce the scattering length and make the dipolar interaction more and more important, yeah, then all of a sudden you start to see new structures. For example, holes in a connected fluid, yeah, just like we saw in the classical ferrofluid, or droplets in a certain arrangement, like a triangular lattice, yes, or, and that's the interesting thing, in the large fraction of that phase diagram, you start to see these labyrinth structures in the ground state of that quantum ferrofluid. Okay, so again, pattern formation in that system where there is a length scale, and we will come back to that length scale in a minute. Yes, where this length scale actually comes from. Okay, so we are motivated by this. Yeah, we find it so funny or so interesting that we want to explore this. Within this talk, I will focus on this left side here, which is called the supersolid droplet regime, yeah, where you basically have a superposition, as I will explain, of a modulated density sitting on some background. Okay, that's what the talk is going to be about only this blue area, and the future work will focus on the even more fun part, basically. Okay. So what is a supersolid? Yeah, and I'm explaining this in just 1D, yes, as to make it simple. Yeah, if you think about a phase diagram where you plot the temperature here and a control parameter, which will be our contact interaction, yeah, the size of these spheres, yes, and you have, for example, a strong dipolar, a strong contact interaction, and you cross that critical temperature for Bose-Einstein condensation, then you end up in an infinite box, yeah, with a flat, boring Bose-Einstein condensate, yeah. But this is already a symmetry breaking transition that comes with a certain phase, yeah, of the condensate that is different every time you do it, and therefore people talk about symmetry breaking of the U1 symmetry, which is just to say that the phase can be any value between 0 and pi and 2 pi. And we are just fixing one in every realization. Okay. Then if you change the control parameter to a supersolid, what's supposed to happen is that this Bose-Einstein condensate gets a periodic modulation, just like these ferrofluids, you know, showed these peaks, yes, these spikes basically, yeah. But this modulation shouldn't go all the way down to 0, yeah, such that these droplets are still connected, such that the whole object has a common phase, yeah. Such that you can talk about the wave function, the macroscopic wave function describing this object, to be a superposition of a flat part, like a normal BEC would be flat, yeah, a fluid part, and a solid part, that's the part that has a periodic modulation. Okay, so that's what I'm going to call a supersolid. We can discuss about the wording and so on if you're interested later on, but I'm just defining it like this. Yes, my wave function should be flat, modulated with a period plus a flat part below. Now you can already see this is a non-trivial state, yeah, because this modulation, if you make a standing wave of matter, yeah, that involves kinetic energy. Yes, so it costs energy to make such a corrugation. So you have to compensate that energy and to make it a ground state by interactions. So you need interactions to make such a wave function the ground state of your system. Okay, and that's going to happen, I mean, via these magnetic dipole-dipole interactions. And there's a long history about you know, the meaning of supersolidity. Originally, it actually comes from the dilute gases, but then it was taken over by the helium guys, yeah, that you know, produced helium crystals by putting helium at very low temperature under high pressure. then you can grow some crystals. And then the question was, is there still maybe a little bit of superfluid fraction left over? And there were even some claims that there would be, but then this was withdrawn again. So for now, we don't know any supersolid state of matter in the world of helium, of solid helium. Yeah, but conceptually, you know, this question was already asked in the 70s. You know, can a solid be superfluid? Was the question. Yeah. For us, actually, the question is a little bit the other way around, because we know we can make a Bose-Einstein condensate, and it is superfluid. We know this. So the question is, can a superfluid be solid at the same time? So it's just the other way around. Yeah. And in order to do this, you have to make this state, and you have to observe various properties. You have to observe, first, of course, that there is a modulation of the ground state wave function. But that's not sufficient. You have to make sure that the phase coherence is maintained all over the place, yeah, so that the whole state has the same phase. And what is more, even if you perturb this a little bit, yeah, by some object or by some excitation, the phase is rigid. Yeah, it sort of stays coherent, even if you perturb it. Okay, that's called phase rigidity or superfluidity in the end. So these are the three things that need to be shown experimentally. So again, yeah, I mean, this instability of a single droplet fragmenting into many droplets can be studied. That's something we did ourselves here. Yes, it's quite funny. Yeah, I mean, you apply the magnetic field, and then, of course, the dipoles want to be head to tail, yeah, because they are attractive, and therefore they lower their energy if they are like this. So the droplet grows against gravity, but eventually it costs so much gravitational energy to make a long droplet even more longer, then it's energetically more favorable to split it in two short ones, yes, or more short ones, yes. That's what you just saw here, yes. So dipolar interaction apparently has this possibility to break the translational symmetry of the system, yeah, because that's what happens, yes. If you go from a flat BEC to a corrugated BEC with a solid part, then there is another U1 phase, U1 symmetry breaking, yeah, namely, you know, where is the origin of my crystal? Okay, and that brings me to the length scale, yeah, which is present in the classical ferrofluids, and very similarly, as discussed by Lewis in the very early papers, also in these quantum ferrofluids, yeah, and that's the so-called Roton length, yes. And you find this figure here in the book by Rosensweig about ferrohydrodynamics already early on. You know, these are these classical fluids where I showed you all these movies from, yeah. And what he plots is basically the energy or the square of the energy as a function of momentum. So it's a dispersion relation, yeah. And you see that if, in this case, you are changing the magnetization, therefore the dipole-dipole interaction, the dispersion relation develops a local minimum at a finite momentum. Finite K means, you know, 2 pi over lambda. Yeah, there is a length scale where the system wants to minimize its energy. And if this touches 0 now, it doesn't cost any energy to have a perturbation that has exactly this period that corresponds to this inverse K here, yeah? Or in this nomenclature KC, yes? So, and that's what happens if you look at the classical ferrofluid, yeah, they make, the surface shows this structure, yeah, and the distance between those droplets basically as a perturbation, at least corresponds to the distance between two such droplets here, or two such density maxima, let's say. Okay, good. But we want to do this in the quantum regime, yeah. And for this, we need some atoms that are magnetic, yeah. So we need atoms that have a large dipole moment, such that the dipole-dipole interaction is important. And of course, we, in addition, have that contact interaction that we want to control with a Feshbach resonance. And both of them come with a length scale. Yeah, they are defined here. And you can compare the two with a dimensionless parameter, which is this epsilon dB. Yeah, and so if epsilon is 0, then you only have a contact interaction, no dipoles. If epsilon is larger than 1, that's how it is defined, then the dipolar interaction is more important than the contact interaction. Yeah, and that can be tuned now with the Feshbach resonance. Yeah, and if you now look into the periodic table, actually, if you look into this length scale here of the dipolar interaction up here, you see that it goes with the dipole moment squared times the mass. Okay, so what do you want to do to optimize this? Is you want to take a heavy atom and an atom that has a very large magnetic moment from the very start, yeah, like due to its electronic structure. And the alkali atoms are a particularly bad choice, yeah, because they just have one valence electron, one Bohr magneton as a magnetic moment. And turns out there are other atoms that are more favorable, yeah, like for example, chromium atoms here have a pure spin magnetism and they have 6 Bohr magneton, yeah. That goes in like the square, so you gain a factor of 36, yeah. And even more, if you go down here to the lanthanides, for example, dysprosium, but you can also take erbium or other magnetic neighbors here, then you see, okay, dysprosium has 10 Bohr magneton, which gains a factor of 100 compared to the alkalis, and it is also very heavy. Yes, it's about twice as heavy as rubidium. Yeah, so you gain a lot in this in the dipolar interaction if you do your experiment with dysprosium. So historically, we started out when Lewis was still in Stuttgart or even before, yeah, with chromium. But as soon as Ben Leff at Illinois, who is now in Stanford, showed us how to cool dysprosium, and later Francesca realized an erbium BEC, we switched over from chromium to dysprosium, and what I'm showing you today is all dysprosium work. Yeah. So how does the experiment look like? Well, that's like your labs also look like. It has nice colors. Dysprosium needs blue and red light for laser cooling. Yeah, I saw the beryllium here, the 313 nanometers. What you see here is 626. So we have actually very much the same light sources as here in the beryllium cooling. Okay, and then we have a glass cell where we actually put some atoms, maybe compose an Einstein condensate, and we can observe it with a microscope objective from the top, such that we can take in situ images of the density distribution. Yeah? And we can tune the magnetic field around to address this Feshbach resonance, and we can shape the trap by various optical dipole trap beams, yeah, just to be able to make a cigar of a certain length or pancake trap, such that we can control all the trap frequencies independently. Genau, and that's the image. So that's how a BEC, a normal BEC looks like, and we can look at it in situ with a resolution of about 1 micrometer. And here comes the Feshbach resonance. Yeah, if we now tune the magnetic field, we are going to change that length scale of the contact interaction, the scattering length. For example, we make it smaller, meaning that we make the epsilon dd larger, yeah, because if you reduce the importance of the contact interaction, the importance of the dipolar interaction increases. And then what happens with the dispersion relation is shown on the right side, just like in this ferrohydrodynamics book by Rosensweig. Yeah, the Roton minimum starts to emerge, and eventually it touches 0. Yeah. Now, at the time, about now 7 years ago or so, yeah, when we started to look at this, the prediction from many our dear theory friends was that if this happens, if you touch the 0 point, the system should become unstable. Yeah, because if you convert a gas that is initially in a pancake like this, the dipoles repel each other. Then they form something and they sit more head to tail, and that eventually produces all of a sudden a negative mean field, and the system with a negative mean field, everything is attractive, should just collapse. Yes, that was the prediction. But then in 2015, we just looked in situ and we saw these pictures, yeah, and they didn't want to disappear. Yes, and you see that there is some structures forming on the surface of the BEC. With a long lifetime, yeah, we can directly evaporate into this. Yeah? And there was no collapse as predicted. Yeah? So something was not quite right with the theoretical description that was just based on a mean field argument. Yeah? Okay, so these are the pictures. So we can see this Rosenzweig instability and there's no collapse. And the question was, why is it stable? In the beginning, in this first paper, we didn't understand. Yeah, we just report the observation. And I remember we spent about 3 months to make sure that we are not fooled by some imaging problems, filamentation of light through a dipolar gas and whatnot. We went through many alternative explanations of that observation that could fool us. Yes. But finally, we submitted the paper and it is published here. And later on, we realized what is going on. Yeah? That is the only slide, I guess, with a little bit elaborate formula here, or with a Schrödinger equation, yeah, that is nonlinear, that now explains the stability. Okay. So what you see here is a Schrödinger equation for a macroscopic wave function psi. Here and here, and you have the usual kinetic term. Yes, you have a trap, a harmonic trap typically. Then you have a two-body contact interaction that goes with psi squared, so that makes this Schrödinger equation nonlinear. Then you have the dipolar interaction. It also is a two-body interaction, so it goes like the density, which is modulus of psi squared. But you see, it's not only nonlinear, it's also non-local, yeah, because this is a long-range interaction, and so you have to integrate over the whole density distribution to get the local mean field. Yeah. Up to this, that was the knowledge of the theory in 2015. On this level, if it would end here, the system should have collapsed. But it didn't. And the reason is that there is a beyond mean field correction now, due to quantum fluctuations, which without any free parameters extends this nonlinear differential equation by a next order term. It goes like the modulus of psi to the third power. Yes, so it depends stronger on the density. Yes, and this term was actually known for contact interaction Bose gases since the 50s. It's called the Li-Huang-Yang correction. And the dipolar term here, which is additive, because fluctuations are always adding up in quadrature. Yes, they don't subtract, they add up. Was calculated by Axel Pelster and Lima. Yes, in a paper. I think I have the reference somewhere. Later on, yes. So what happens? We have two mean field terms, this one and this one, and they can have opposite sign. One can be positive, repulsive, and the other one can be attractive, negative. Yeah. So if they just happen to be, let's say, almost equal but with opposite sign, then the mean field essentially vanishes, and the next order term becomes important. Yeah, like this term, which is normally totally negligible because we are working with a very dilute gas. This term is usually totally unimportant. Yeah, but if for certain parameters, yeah, and we are tuning this very precisely, these two terms almost cancel. Yeah, then this term becomes important. Yeah. So what is this? Well, if you think about the Bose-Einstein condensate, that's my hand waving argument, and Louis, you close your ears. Then you have elementary excitations, namely phonons. Yeah, every phonon is a harmonic oscillator. Every harmonic oscillator has a 0-point motion, 0-point energy, and if you integrate over all these phonon modes and its 0-point fluctuations, yes, then you end up with a repulsive term in this energy functional. Okay, that actually stabilizes, because it's repulsive, something that wants to collapse. Okay. There's a plus sign here, and note that all these numbers here are not free parameters. They are already there somewhere further up, yes, like the scattering length, the epsilon dB, and so on, the G. There's no fudge factor, yes, that we could use to explain it. Yeah, the only thing that needed to be done was to get these factors 32/3 and so correct. Yeah, remember this, yes. Okay. Beyond mean field effects. Yes. So what is the situation? Yeah, we have a dipolar mean field, let's say, that is attractive, contact mean field that is repulsive. They are very large, but opposite. So that means this very small Li Huang-Yang correction, yes, actually becomes important. It's repulsive. Yeah. This is the original paper, and yeah, here is the theory of for the dipolar gases. Exactly. So that's the term that saved us. Yeah, quantum fluctuations in the end. So yes, because the combined mean field is very small. Yeah, and then this green arrow, which is the Li Huang-Yang, actually becomes important. Yeah. So this leads actually to self-bound states. Yeah, because it's higher order. Yeah. So you see that if you have a little bit of an attractive mean field, it wants to shrink the whole system. It gets smaller and smaller, but the Li Huang-Yang, the fluctuations increase faster, yeah, and then there is a minimum, and the system stabilizes at finite density. Okay, so this is another way of writing exactly the same equation with this psi3 term, which is due to quantum fluctuations. Yeah, and on the right side you see experimental data of such a single droplet now that you can isolate that is forming as we are changing the parameters. So due to that term, something interesting happens now. Yeah, because if you now just add atoms to a single droplet only, let's say a single self-bound object, which we call a droplet, then what happens is that the density first increases and reaches a saturation density, and from that point on, the droplet just grows. Yeah. Which is what you know from a normal water droplet as well. Yeah, you add some molecules and the droplet just gets larger. The density stays constant. Yeah, that's normal for a liquid or for a droplet, yeah, of classical fluids, but that's not normal for a Bose-Einstein condensate, right? So in that sense, this is now a real fluid. Yeah, I mean it's not no longer just a gas like a Bose-Einstein condensate is a gas that can have superfluid properties. So it's liquid-like, yes. And the self-bound droplet can be produced in our vacuum chamber, yes, with certain procedure. We can make one, and it will not expand, yes. Even if there's no trap around and so on, so we can make a droplet, just like a water droplet or a helium droplet, that just floats in our chamber happily, yes, as a bound state. Yeah. That's the corresponding experiment where you see that this droplet stays there, and eventually, if the number of atoms in the droplet reduces below a certain critical number, evaporates, yes, and makes a transition from a liquid to a gas. And this kind of physics has also been confirmed in the group of Francesca Ferlaino then in Innsbruck, and also by a number of groups that are working with mixtures of alkali atoms, starting with the experiment of Letizia in Barcelona. Marco Fattori's group is working on this, Dajun Wang and others. And I think here you also, at least for some time, you had some ideas in that direction, but okay. Anyway, so this concept of quantum droplets that are stabilized by quantum fluctuations is by now a research field in itself, basically, ranging far beyond the dipolar gases. Yes, it is a very general concept that actually was theoretically predicted by Dima Petrov already in 2015. So you can play around with this. Yeah, so for example, you can make a few droplets and just release them in a waveguide. Of course, if they are magnetized like this, they will repel each other and fly apart, just like classical ferrofluids droplets would also do. Yes, You see this here. You can kick them, yeah, and make them oscillate like in a Newton's cradle, if you like. Yeah, that's a lot of fun. Yeah, you can have with these droplets. So as I said, this is a research topic in its own right. If you want to read more about this, there's, for example, a nice review by Igor, who was a postdoc with us in Physics Today. But we wanted not only to talk about droplets here, but also about supersolids. Yeah? So that is now a single droplet. And now we want to make an array of these droplets, yeah, and connect them to a supersolid. Yeah? So how can this be done? Well, I mean, very early on, yeah, we have seen pictures like this, yeah, where we see that along a certain direction, there's a modulation, yes. But so the in situ observation seems to indicate, yeah, there is a supersolid. Yeah. But as I said, you need to do 3 things to confirm that you really have a supersolid. It's not enough to just see the modulation in situ. You should also check for phase coherence and for phase rigidity, like the superfluid stiffness. Yeah. Let's ask first, how do you make from one droplet many droplets? Well, we have seen that movie. Yeah? We remember this droplet got longer and longer, and eventually it was energetically more favorable to split into 2. So what does this mean? Well, if you have a droplet like this and you push it, it costs more and more energy. If you increase the confinement along the long axis, then eventually it's more favorable to split into 2. Yeah? So that's what we calculated 5 years ago or so. Yes, if you just take an array of, like say, 1 droplet and you squeeze it in one direction, it should split up into many droplets. Yeah, just like, again, looking from the top on one of these ferrofluid experiments, this droplet, a single droplet, splits into 2 or many. Yeah? On the left side, you see the classical. On the right side, the quantum simulation. I mean, the Gross-Pitaevskii simulation of a dipolar quantum gas. Yes, and if you do the simulation, you can even encode the phase of the wave function here in the color. Yes, and you see that, okay, after some time, sort of the phase even equilibrates to the same value. Yes. So that comes back to our definition. Yeah, I mean, what do we need to have? We need to have a finite fluid. So it's not enough to just have an array of droplets, which would let the density go to 0 in between. Yeah? Then if this would be the case, they would quickly lose their phase coherence, yeah, because they are independent objects. They should be connected, yes, by a fluid part. Yes. So if you do the calculation, you solve for the ground state of that Gross-Pitaevskii equation. You change the scattering length, make it smaller. You start with the Bose-Einstein condensate on the right side that is flat. And eventually, in your theory calculation, you observe that the ground state should start to show a little bit of a modulation with some background. And if you go too far, then these droplets are actually separating. Yes, and it's just a solid, no longer super. Yes. And that's the experimental observation in situ, yes, for these parameters. So we can reproduce again the predictive power or the predictions of that Gross-Pitaevskii equation. But of course, we need to check for phase coherence. Yeah. And one way to do this is to just let it expand. Yeah. If you have a periodic modulation, you expand it. It's not so simple, but in first approximation, think of a diffraction experiment. Yes. You have a periodic light field that is modulated by a grating or so. You go to the far field and you see a diffraction pattern. Yeah? And something like this happens here. Yeah, this is the in situ pattern, and you go after time of flight into momentum space, and you see that there is not only a 0th order, but a 1st order peak on the 2 sides. If you look a little bit closer, you even see that there is something in between. Yeah? So these peaks are signaling the coherence if you measure them many times. Yes, so you have to do statistics over many of those realizations. And then these peaks here show you something about the next neighbor coherence. And the in-between peaks here at this position, they show you something or tell you something about the next neighbor coherence, okay? And I should say there was a related work on this time of flight expansion by the Pisa group, Giovanni Modugno's group, and again, the Innsbruck group by Francesca. We have measured a phase diagram this way, where we not only look for the density modulation as a function of scattering length and atom number. So this is experimental data. And we basically do a Fourier analysis of images like this, where we see that the modulation starts below a certain threshold, yeah, where we have a BEC, and on the left side we have droplets, but we don't know yet are they phase coherent or not. But then we do this time of flight expansion, and we can extend that phase diagram to a diagram that also contains the next or the nearest neighbor coherence. And you see only very close to that transition point here, we actually do see phase coherence, and we lose it if we go too far. Yes, although it looks like droplets on the left side, eventually they lose their connection, and we are no longer in a supersolid state. Yeah? So this can be separated into Bose-Einstein condensate, coherent crystal or supersolid, or isolated droplets. So that's nice, but we have still one more thing to do. And that is the test of superfluidity, because superfluidity requires that you perturb the system or excite it a little bit, and you should still see phase coherent evolution. Yeah. Okay, and one thing that one should keep in mind, yeah, when you do investigate such phase transitions, is the very general theory of phase transitions, which for a symmetry breaking transition like the one that we have here can be described by a complex order parameter in a Mexican head potential. Yeah, so I mean, even the transition from a thermal cloud to the BEC can be described in this kind of language. Yeah, where you start at high temperature, you have a free energy that just goes quadratically with the order parameter, and there's zero order parameter in the beginning. Then you come to the critical temperature, and the system basically rolls into a minimum, let's say here, and chooses a certain phase along the rim of that Mexican head potential. Yeah, that's the U1 symmetry breaking here. Yeah, and whenever you have such a symmetry breaking going on, there are characteristic excitations, characteristic modes associated with this. One is the Goldstone mode, yeah, which for the normal BEC are just the phonons in the Bose-Einstein condensate. Yes? And the other one is the Higgs mode. We can talk about the Higgs later. That is an excitation. So this Goldstone mode is gapless. It basically lives on the rim itself. It doesn't cost any energy, at least for infinite wavelengths. Yeah? Whereas the Higgs mode costs energy. It has a gap. Yeah? It's like a harmonic oscillator in the orthogonal direction. Now, in the supersolid, we have two symmetry breaking processes going on at the same time. Yeah? Namely, the phase of the BEC is a broken phase, and the translational symmetry due to the formation of that crystal is also a symmetry breaking process. Yeah. So if you go back to your solid state physics, yeah, what is the Goldstone mode of a crystallization? what would you say is the Goldstone mode in a crystal? Huh? Translation by electron. Yes, so it's like the normal phonons. Yes, the crystal phonons. Yes. The zero wavelength phonon doesn't cost any energy. The infinite wavelengths, 0K, it just shifts the whole crystal to the side and doesn't cost any energy. Yes. So the Goldstone mode of a solid is the phonon in the solid. Yeah. So now we have two kinds of phonons here: the BEC phonon and the crystal phonon. Yeah. And turns out, yeah, if you have two such symmetry breaking processes at the same time, you have two Goldstone modes, yeah, but they can be a combination of the two phonons that we are talking about. And in this case, you can have a phonon in the BEC and a phonon in the crystal that are in phase, which mean that both the density in the BEC and in the crystal are like compressed at certain places and decompressed at other places. That's the compression mode of a supersolid then. And there is the other more interesting one where the BEC phonon, for example, decompresses at a certain place and the solid compresses such that the local density stays constant. And this is the mode that is not responding to the compressibility of the supersolid, but to the superfluid stiffness, to the rigidity. So this is the interesting mode, the out-of-phase oscillation between the BEC and the crystal phonon. And that's the one that we have observed. Yes. So that's the Goldstone mode, which we can see in real space. Yeah. So here's a calculation. What does it mean? It means that the crystal is moving in the trap from left to right, while the BEC is moving from right to left. Yeah? So they are basically oscillating like this, such that the center of mass of the distribution is not excited. That, in principle, if you go to the thermodynamic limit, doesn't cost any energy. Yes? And that's the interesting mode that basically proves superfluid stiffness or rigidity. And here you just see some experimental realizations. You know, if the center, I mean, that's always sort of the center of the distribution. Here's a symmetric picture. And then if you move it a little bit to the right side or the left side, then the weight of the different droplets has to change. Yes. Just like shown in this little movie here. Yes. Okay. So this experimental observation of that Goldstone mode, at least for us, was satisfying because it really proves that this new state of matter fulfills all the three criteria that a supersolid should show. Yes. Okay. And that brings me to the outlook, which where I show you this picture again. That's the phase diagram, and what we have looked at is the supersolid, this blue thing here. Actually, we have looked at this only in one dimension. We can talk about 2 dimensions as well. First experiments in Innsbruck, for example, show that there might be a chance to see the supersolid here also in 2 dimensions. But what I find personally even more interesting is to enter this regime where these labyrinths show up as a highly degenerate ground state of such a many-body system. Yeah? And for this, we have actually changed our setup because, as you can see, here is an atom number, and the atom number is 200,000 or something like this. So it's a big condensate that is required to observe this. And our setup actually that we had is still an old chromium setup from the very old times, and it couldn't just produce enough atoms in the BEC. And so we changed it. We have built a new apparatus. It's coming online now, so watch out or stay tuned. And that's what we are aiming at, to observe these funny structures in a superfluid state that is connected. For example, this one is, everything is connected here, yes, but it still has interesting self-organized structure formation. Okay. And with this, I'm at the end, and thank you for your attention. And I wanted to thank also the whole team here, especially Martin Zwierlein, who spent a lot of time with us during his sabbatical. Yeah, and you for your attention.